During this discussion, I will show you how to prove the theorem limit x approaches to a, x to the nth power minus a to the nth power divided by x minus a equals n times a raised to the n minus first power. After discussing the proof of the theorem, I will also show you how to work two examples using this theorem. Alright, first we will look at the proof of the theorem. Now I need you to look at the numerator xn minus a to the n. That is a polynomial whose order is equal to n. Remember, order of a polynomial is the highest exponent. If I go ahead and replace x equals a in that polynomial, you can see that it becomes a to the n minus a to the n, which is equal to 0. That means x equals a is a 0 of that polynomial. If x equals a is a 0 of that polynomial, according to the factor theorem, we know that x minus a should be a factor of that polynomial, xn minus an. And we already figured out one factor. That factor is x minus a. Remember, we are looking at the polynomial x to the n minus a to the n. When I factor out the first order x minus a, what should be the order of the remaining polynomial? The order of the remaining polynomial should be n minus 1. In order to create that x raised to the nth power, this x has to be multiplied by x to the n minus first power. When I multiply this x with x to the n minus first power, I can get x raised to the nth term. However, in addition to that term, I will also have to multiply a and x raised to the n minus first power. When I multiply those two terms, I'm going to create an unnecessary term, which is negative a x raised to the n minus first power. I need to get rid of that term. To get rid of that term, the remaining polynomial right here needs to have a term which will eventually create a positive of this term a x n minus 1. I need plus a x n minus 1. But how do I create this term plus a x n minus 1? In order to create that, I can pay attention to this x once again. That x has to be multiplied by a times x raised to the n minus 2 in order to create the term right here. Alright, let me write it down as that. I will need a plus a times x raised to the n minus 2. When I have that, you can see when this x is multiplied by this whole term, we get a times x raised to the n minus first power as a positive term. Therefore, these two terms will be cancelled off. However, while those two terms are cancelled off, I'm once again creating another unnecessary term. That unnecessary term is created by multiplying this negative a with a times x to the n minus 2. What's the term that's being created when you multiply those two? We are creating a negative a squared x raised to the n minus 2 term. Now, just like earlier, I need to get rid of that term. In order to get rid of that term, I will need a plus a squared x raised to the n minus 2, which we can create by paying attention on this x again. That x will have to be multiplied by a positive a squared x raised to the n minus third term. Then we can create this term right here. Alright, let me write it as that. I'm going to need a plus a squared x raised to the n minus 3. Now, these two terms are cancelled. However, while those two terms are getting cancelled, I have also created another unnecessary term. That is by multiplying this negative a right here with the term right here. When I multiply those two terms, we get negative a cubed x raised to the n minus 3 term. Once again, we need to get rid of that term as well. To get rid of that term, I will need a plus a cubed x raised to the n minus 3. In order to create that term, I can look at this x right here, just like earlier. That x will have to be multiplied by a cubed times x raised to the n minus 4. Then I can create the term right here. So let me write it as that. I will need plus a cubed x raised to the n minus 4. Now we can get rid of these two terms. While getting rid of those two terms, we have once again created an unnecessary term. That will also have to be removed from the polynomial. Alright, now I don't want to show all of those work again. You can simply look at this sequence and write down the remaining terms. Let's say we are going to write down two more terms. What should be the next term inside this polynomial? It will be a plus. We can see that the power of a is getting gradually increased. So the next term must have a raised to the fourth power. A raised to the fourth power. Now what happens to x? X had n minus 1, x had n minus 2 next, x had n minus 3, x had n minus 4. That means our next term should be x raised to the n minus 5. So let me write it as that. X raised to the n minus 5. If you need, would you like to write another term? Well, of course, the next term will be even easier. We can write it as a raised to the 5th power, x raised to the n minus 6th power. Likewise, we can keep writing those terms. How many terms I will have to write? I will have n number of terms. And what should be the nth term? As you can see, what happens to a? There was no a term right here. There is a to the first power on the second term. On the third term, we had a raised to the second power. On the fourth term, we have a raised to the third power. On the fifth term, we have a raised to the fourth power. Likewise, on the nth term, we will have a raised to the n minus 1 as the power. What will be the power of x? Look, the first term had x raised to the n minus first power. The second term had x raised to the n minus second power. The third term had x raised to the n minus third power. The fourth term had x raised to the n minus fourth power. That means the nth term must have x raised to the n minus nth power, which is x raised to the 0th power. That means this last term will not have a component from x. There are some other ways also to do that argument. This polynomial has just two terms. One is x to the nth power, which we created by multiplying this x with x raised to the n minus first power. The other term we have is negative a raised to the nth power. We can create that one by multiplying this negative a with a raised to the n minus first power. That way also we can conclude that this polynomial has n number of terms. If I wanted to write the term before this last term, what will that look like? Another plus sign. It will be a raised to the n minus second power, and there will be a first order x. I hope you can see the reason behind writing that term as that. Alright, now let's continue. Now here we have this function on the left hand side. I need x to the nth power minus a to the nth power to be divided by x minus a. Look at this. If I divide this polynomial by x minus a, this is going to be the quotient. Alright, let me write it as that. So this leads to x to the nth power minus a to the nth power divided by x minus a being equal to all of that. So let me copy and paste that part. I would like to have it in red. Now what I have to do is I need to obtain the limit x approaches to a for this function. So let's go ahead and do that. We need the limit x approaches to a. The left hand side we have x to the n minus a to the n over x minus a. We showed that it is equal to all of this. Therefore, instead of taking the limit of this rational function right here, I'm going to take the limit of all of this on the right hand side. So let me write it down as that. I will have this being equal to limit x approaches to a, all of this. And I would like to have it in blue. Now we can begin the direct substitution when I replace x equals a for each term. The first term right here becomes a raised to the n minus 1. And then we have a plus. How about this second term? It will be a times a raised to the n minus second power. Those two will be simplified to become another a raised to the n minus first power. Because when you multiply two quantities with the same base, the exponents are getting added. Alright, now look at this third term right here. We have a squared times x raised to the n minus 3. When that x is replaced by a, it is a squared times a raised to the n minus third power. Those two will also be simplified to become a raised to the n minus first power. And it's going to be exactly the same with each of the other terms as well. Look at that fourth term. It's a to the third power times x raised to the n minus fourth power. When that x is replaced by a, that term becomes a to the third power times a raised to the n minus fourth power. Then when you simplify, that also becomes another a raised to the n minus first power. Likewise, you can see that characteristic with each of the terms in that polynomial. Even the last term, everything is going to be just a raised to the n minus first power. Now my question is, how many such terms we have? We have n number of terms. A raised to the n minus first power is added n times. It should finally reduce to n times a raised to the n minus first power. This is the complete proof of the theorem right here. Now we will do a couple of examples. Here is your first example. Let's say I need to evaluate the limit x approaches to say 3 from the right hand side. X raised to the fifth power minus 243 divided by x minus 3. Please note that for this example, x approaches to 3 from the right hand side. Well, for the theorem, it was not specified whether x approaches to a from right hand side or left hand side, but that has nothing to do with this result. Why? That is because the theorem is given as limit x approaches to a for this function. That indicates that the limit x approaches to a from the negative side exists, and limit x approaches to a from the positive side also exists, and those two are equal to each other for this function right here. Therefore, whether the given question has a right hand side limit or a left hand side limit, or whether that side is not specified, no matter what, that theorem can be applied without any issues. This question can be rewritten as limit x approaches to 3 from right hand side, of course, x raised to the fifth power minus 243. Of course, you can write it as 3 raised to the fifth power, that divided by x minus 3. Now that's a very similar situation to our theorem. The theorem was limit x approaches to a, x to the n minus a to the n divided by x minus a. That was equal to n times a raised to the n minus first power. Now for this problem, of course, we have x raised to the fifth power. That means your n is equal to 5 for this example. And then instead of a raised to the nth power, we have 3 raised to the fifth power. Therefore, your a for this example is equal to 3. Of course, if I know n and a, then I'm done. I can directly write down the final answer. Therefore, the final answer right here should be equal to n times a raised to the n minus first power. N is equal to 5, that times a, which is 3, raised to the n minus first power, 5 minus 1. Therefore, this can be simplified to become 5 times 3 raised to the 4th power. We need to do some further simplifications. This is 5 times, what is 3 raised to the 4th power? It's 81. Therefore, I need to find 5 times 81, which is 405. That's the final answer for this example. Let's do another example. Let's say we need to evaluate the limit x approaches to 2. This time I'm not going to specify whether x approaches to 2 from the left hand side or from the right hand side. Here's the question. On the numerator, I have x raised to the 4th power minus 16, and in the denominator I have x raised to the 6th power minus 64. Now, can you apply that theorem for this question as well? In the given format itself, we may not be able to apply the theorem. Let me rearrange this question a little bit, and then we can do a small modification, and after that we can apply the theorem. Look at this. I'm going to rewrite this as limit x approaches to 2, the numerator, just like earlier, we can write x to the 4th power minus, we know 16 can be written as 2 raised to the 4th power. X to the 6th minus 64 can be written as 2 raised to the 6th power. Now, in that form itself, I cannot apply our theorem because the theorem requires a little bit of a different format. Here is the theorem again. Limit x approaches to a, x raised to the nth power minus a raised to the nth power divided by x minus a. This is equal to n times a raised to the n minus first power. So please note that the denominator right here is a first order polynomial x minus a. For this question, the denominator is a 6th order polynomial. Therefore, I cannot apply this theorem as it is for this question. Therefore, I need to modify that question. This is what I'm going to do. I will continue this question this way. Limit x approaches to 2. In the numerator, I have x to the 4th power minus 2 to the 4th power. That's true. In the denominator, I have x to the 6th power minus 2 to the 6th power. That's true. What I'm going to do is, I'm going to divide both top and bottom by x minus 2. When I do that, I can apply our nice theorem separately for the numerator and for the denominator. Then we are done. Therefore, let me go ahead and apply our theorem for the numerator. So here's our numerator. For that numerator, can you identify n and a? N is equal to 4, a is equal to 2. Therefore, we can write down the right hand side for the numerator as 4 times 2 raised to the 4 minus 1. That has to be divided by, here's the denominator. For the denominator, your n is equal to 6 and a is still equal to 2. Therefore, let's go ahead and apply the theorem for the denominator. Then it becomes 6 times 2 raised to the 6 minus first power. Alright, now we need to do the simplification. So when I simplify that, I get 4 times 2 raised to the 3rd power on the numerator, and that has to be divided by 6 times 2 raised to the 5th power. This will be simplified to become 1/6. So this is our final answer for this problem. If you have any questions, please feel free to let me know. Thank you so much.